And welcome to the final topic of this solutions unit, how to change the melting and boiling point of water by adding a solute to it. This is colligative property. How do you change the phase change temperature? Well, you might recall way back 100 years ago when we did phases and phase change, that water, pure water, at STP is going to melt, I should say at standard pressure, will melt at 0 degrees Celsius, which is 273 Kelvin, and boil at 100 degrees Celsius, which is 373 Kelvin. But you're not stuck with those melting and boiling points. Well, if you want pure water, you're kind of stuck with the melting point. The boiling point you can change using pressure. Increasing pressure will increase the boiling point. Decreasing pressure will decrease the boiling point. So we can mess with these intermolecular attractive forces, and using pressure, we can sort of artificially increase those attractive forces to keep water a liquid for higher temperatures. The other way you can do it is by adding a solute to water, and this will interfere with the attractive forces as well. It will make the boiling point higher by weighing down the water molecules, requiring it more energy to break free and form a gas. In a solution, water molecules are more attracted to the solute than they are to each other. And therefore, it's going to take a temperature higher than 100 degrees to get the water to boil. And it will decrease the freezing point because in order to freeze, the water molecules have to come together in a crystal lattice, and the ions get in the way of that, which means you have to cool it down even further to get the water to freeze. So the boiling point goes up and the freezing point goes down, and the more solute you add, the more pronounced this effect will be. So for every mole of dissolved particles, the boiling point of water will go up by 0.52 degrees Celsius. And for every mole of dissolved particles, the freezing point depression will decrease by 1.86 degrees Celsius. This, by the way, these calculations are not on the reagents, but if you're taking an advanced class, you may have to calculate it, so I'll show you how it's done. So here's a practical example. This is calcium chloride, and calcium chloride can be put on sidewalks to melt ice. You may have seen this. They're the little white pellets. Like if you're walking into school after a 2-hour delay, you might find these white pellets scattered all over the sidewalk of your school. Calcium chloride does a really good job of lowering the freezing point of water so that water can remain a liquid even at temperatures that would normally freeze it. And this prevents ice buildup on the sidewalk. You may have seen a truck going by during snowy conditions that's scattering salt water onto the roads. And this salt water will mix in with the snow, lower the freezing point, and prevent the water on the roads from freezing, preventing ice. Now, calcium chloride does a tremendous job, but it's very expensive to use for roads. Salt is a lot less expensive. However, you'll find that in states that have a lot of snow that use salt on the roads, you have an increase in the corrosion of the undersides of automobiles. So when you're driving around in the wintertime, make sure you get your car washed to get all the salt off your car, and make sure you get an undercarriage wash to get all the salt out from the underside of your car so that, for example, your tailpipe doesn't rust. Here's another practical example: antifreeze. In your car's engine, you have moving parts, very fast moving parts that generate a lot of heat. This heat could actually cause the parts in the engine to seize up. So to prevent that from happening, water coolant is pumped through your car's engine to keep your car's engine cool enough so that the metal parts don't overheat. The water absorbs the heat from the engine, goes out to the radiator where the heat is emitted, and cooler water is recycled back into the engine. However, This water that passes through the engine, especially under particularly hot conditions and high strain on the engine, like for example, going up the mountain pulling a trailer, your engine could actually overheat because the water in the engine begins to boil. So, antifreeze is used to raise the boiling point of water inside that system. But even more importantly, if you live in very cold environments, especially if you park your car outside in temperatures that are colder than freezing, the water in your car's engine would freeze. And when water freezes, it expands. And this can crack your engine block. It can blow all your seals. And so when it thaws, you'll find all of the fluids, your transmission fluid, your power steering fluid, your oil, just all on the ground. And you'll require several $1,000s worth of repairs at the shop. Antifreeze will lower the freezing point of the water in your cooling system to such a degree that you don't have to worry about that water freezing. Now, there are some places in this country, like North Dakota in the middle of the winter, where it gets so cold, you actually have to put what's called a block heater on your engine. It's basically a blanket that you put on your engine, an electric blanket, to keep the engine warm enough so that it won't freeze. On the back of your antifreeze bottle, you'll see a chart which will say, if depending on the size of your cooling system in quarts, how many quarts of that cooling system should be antifreeze in order to protect your car's engine down to a certain Fahrenheit temperature. So, for example, if your car's engine has a 10-quart cooling system, which you can find out if you look in your owner's manual for the car, if you want to protect your car's engine down to minus 34 degrees, make sure that half that cooling system, 5 liters, is antifreeze. Let's say you don't live in an environment where it's going to get that cold. Maybe you only need to protect down to minus 12 degrees Fahrenheit. Well, in that case, 4 liters out of the 10 liters should be antifreeze. So this chart can help you to determine how much antifreeze you need to add in order to protect down to a certain temperature. Now, antifreeze does not do a great job of moving heat away from the engine. So in the summer, you're going to want to have your system purged if you put extra antifreeze in the winter, and have more water put in because the water does a better job of carrying heat from the engine. Not only will it lower the freezing point, it will also raise the boiling point. But you can see the effect on the freezing point is far more dramatic than the effect on the boiling point. Here's how particles enter into it. Electrolytes, which are ionic, will break up into ions when you dissolve them in water and conduct electricity. But these actually add extra particles to the water, increasing this effect of changing the melting and boiling point. Sodium chloride, when dissolved in water, breaks up into sodium ions and chloride ions, which means that 1 mole of salt will dissolve into 2 moles of dissolved ions. Dissolving iron 3 nitrate in water will result in the formation of iron plus 3 ions and nitrate ions. But notice that dissolving 1 mole of iron 3 nitrate in water will have the effect of yielding 1 plus 3 is 4 moles worth of ions in the water. Which means if you dissolve iron 3 nitrate in water, it will have twice the impact on the melting and freezing point as sodium chloride has. The melting and boiling point, as sodium chloride has. Because the more ions there are dissolved in the water, the greater this effect will be. Non-electrolytes, which are molecular, are not made of ions and therefore do not break up any further when you dissolve them in water. They also don't conduct electricity because there's no charged particles. An example of this would be glucose. When you dissolve glucose in water, 1 mole of glucose will yield 1 mole of dissolved particles. Dissolving salt in water will have twice the impact as dissolving sugar. So, why don't we put salt in our car's engines? Well, because salt can corrode the inside of our car's engine. That's why we don't use it. We want to use a substance that's both going to raise the boiling point and lower the freezing point without corroding our engine out from the inside. What we do use for antifreeze is this stuff here. This is ethylene glycol. This is that sort of yellowish green liquid. You got to be really careful with that stuff. Ethylene glycol is highly poisonous. It has a sweet taste, but as it gets metabolized by the body, it forms these razor sharp needles in your kidneys that essentially liquefy your kidneys and you bleed out from the inside. It's a horrible, painful way to die. So make sure that when you store antifreeze, it's always on a high shelf. And if you see any of this telltale yellowish green liquid, that you clean it up immediately. And especially keep your pets away from it. By the way, if your pet accidentally licks some up, you get them to the vet immediately. There is an antidote that they can give them that will change the metabolism of the antifreeze and allow for the antifreeze to be passed through the body without forming these razor sharp crystals. When you dissolve 1 mole of antifreeze into water, you'll get 1 mole of dissolved particles. So the impact on the melting and boiling point is not as strong as if you were using something ionic, but you don't want anything ionic inside your car's engine. The more particles you have dissolved, the higher the boiling point and the lower the freezing point will be. So if we look at these 4 solutions, which one will have the highest boiling point? Well, the highest boiling point will be the one with the highest concentration. The highest concentration will have the greatest number of moles dissolved in the least amount of water. Therefore, choice 1 will have the highest boiling point. Which one will have the lowest boiling point? Well, boiling point will be lowest if it's least impacted. And this will be the lowest concentration, which would be the least amount of solute in the most amount of water, the most dilute solution. By the way, when you're dealing with multiple choice questions and you're asked the highest, the lowest, the greatest, the weakest, the strongest, these are what are called extreme questions. And extreme questions always have extreme answers, which means you can eliminate any choice that's not extreme. Choice 2 and 3 have medium concentration. We can immediately eliminate those 2 choices. If the question is extreme, then your answer will be either the highest extreme or the lowest extreme, nothing in the middle. And this will help you to eliminate possible choices. Which one has the highest freezing point? Well, adding solute will lower the freezing point. So this is asking which one will lower the freezing point the least, which would be the one with the lowest concentration, again, 4. And the lowest freezing point will be the one that also has the highest boiling point, 1, the one with the greatest concentration. Based on these 4 solutions, now notice that our moles are identical and our grams are identical. The only difference is what our solute's formula is. Choice 1 is a non-electrolyte. It's made only of nonmetals, which means dissolving 1 mole of this will result in only 1 mole of particles. Choice 2 is ionic and breaks up into potassium ions and chloride ions. So dissolving each mole of potassium chloride will result in 2 moles of ions. Dissolving magnesium nitrate in water will yield 3 moles of ions per mole of solute. And dissolving lithium phosphate in water will produce 3 lithium ions and 1 phosphate ion for a total of 4 dissolved ions. You might say, well, aren't there 4 phosphates? No, because if there were 4, this would be in parentheses, just like this is, and right? So there's only 1 phosphate and 3 lithiums. 1, 2, 3, 4 dissolved ions. So either choice 1 will be right, or choice 4 will be right. We can immediately eliminate choices 2 and 3. Choice 1 will affect the boiling point and freezing point the least. Choice 4 will affect the boiling point and freezing point the most. So which one has the highest boiling point? The one with the most ions. Which will have the lowest boiling point? The one that doesn't break up to form ions. Which will also be true of the highest freezing point. Which has the lowest freezing point? Whichever one breaks up into the most ions. The more ions there are, the higher the boiling point will be, and the lower the freezing point will be. Now, let's actually calculate this. Remember, the boiling point rises by 0.52 degrees Celsius per mole of dissolved particles, where the freezing point decreases by 1.86 degrees Celsius per mole of dissolved particles. M will be the molality of the solution. I will be how many particles it breaks up into. For non-electrolytes, it will be 1. For the rest of them, it will be however many ions it breaks up into. So for boiling point elevation, we'll use this formula. The change in boiling point temperature is equal to the number of dissociated particles times 0.52 degrees Celsius per molal times the molality. The freezing point depression will be the number of dissolved particles times 1.86 degrees Celsius per molal times the molality. This will be how much the boiling point changes by and how much the freezing point changes by. All right, let's use them. By the way, in my class, you have AE reference tables. These values can be found on reference tables A and B. Okay, so what is the boiling point of a 3 molal solution of antifreeze? So first we set up the formula. How many particles does C2H6O2 break up into? Well, they're all nonmetals, so it doesn't break up beyond itself. So therefore, there's only one particle. So the value for I will be 1. So let's substitute in the numbers. There's one ion, well, one dissolved mole of particles, times the boiling point elevation constant is 0.52 degrees Celsius per molal, and our concentration is 3 molal. And if we multiply it across, molal cancels out and gives us 1.56 degrees Celsius. Now, this is not the boiling point. Remember, this is the change in the boiling point temperature. Water normally boils at 100 degrees. This is telling us that it's changing by 1.56 degrees. So the boiling point will be 101.56 degrees because our temperature change will increase the boiling point by however many degrees we calculate. What's the freezing point of a 2 molal solution of calcium nitrate? Well, again, we set up the formula. We figure out how many particles calcium nitrate breaks up into, and since there's 1 calcium and 2 nitrate ions, it breaks up into 3 particles. So we'll put 3 in for I. The freezing point depression constant is 1.86 degrees Celsius per molal, and we have a concentration of 2 molal. So when we multiply, molality cancels out. When we multiply across, we get 11.16 degrees Celsius. But once again, this is not the freezing point. This is the change in the freezing point temperature. And since water normally freezes at 0 degrees Celsius, this is going to tell us how much the temperature changes below 0. So our new freezing point will be negative 11.16 degrees Celsius. And that's how to find the freezing point and boiling point of a solution and how to predict what the change will be to the freezing point and boiling point. That is all for this unit. The next unit we're going to do is on acids and bases. Until that time, be well, be happy, be cheerful, find something interesting to do, hug your puppy, kiss your kitty cat, or whatever else, I don't know, pet your pug. Maybe you have an ocelot somewhere out in the garage. I don't know. I don't know you. I don't know your life. You could have a hedgehog. If you have a hedgehog, good for you. But, they're a bit spiny, but they're really, really cute. Anyway, bye.